our last speaker is Professor Xiaoguang. Professor Li Xiaoguang is a professor of biological and medical engineering at Beihang University and director of the Beijing Key Laboratory and the International Science and Technology Cooperation Base. He will discuss bioactive materials-mediated neuroprotection and neurodegeneration, a therapeutic strategy for glaucoma. So it's a pity that due to the last-minute schedule conflict, Professor Li cannot come to Hong Kong, but he asked his team member, Mr. Liu Xiao, to present on behalf of him. So let's welcome, please.
Good afternoon, everyone. The title of my presentation is Bioactive Materials-Mediated Neuroprotection and Neuroregeneration, a therapeutic strategy for glaucoma. This work was accomplished with the joint support of Professor PISO, Professor Ningli Wang, and Professor Sheng Liu. Blinding optic neuropathies are relatively common in clinical practice, primarily including glaucoma, optic nerve glioma, and traumatic optic neuropathy. These diseases all cause damage to the optic nerve and the death of RGCS, thereby impairing visual function. Optic neuropathies have a high blindness rate. Currently, there are approximately 17 million blind individuals in China. Glaucoma is the leading cause of blinding optic neuropathies globally. The number of individuals with glaucoma stands at 87 million, with 21 million in China alone. The primary treatment approach for glaucoma involves lowering the IOP. However, simply reducing the IOP does not fully halt disease progression. RGCS protection and regeneration are currently focal points of research. To address these issues, Professor Xiaoguang Li has developed a type of bioactive material. This bioactive material combines chitosan with neurotraffic factors and is capable of sustainably releasing neurotraffic factors for up to 10 weeks. Its non-toxicity, biodegradability, and excellent biocompatibility handle it with high clinical translation potential. Firstly, we established an IOP elevation model in adult mice. We injected silicon oil into the anterior chamber angle, and the IOP reached 38 mmG after 3 days, then decreased to 30 mmG after 1 week, and remained elevated for more than 8 weeks. Following the increase in the IOP, RGCS gradually died over time, with only 60% of RGCS surviving at the 8-week mark. In the NGF-chitosan group, we injected NGF-chitosan into the vitreous body of the eyeball 1 week after the elevation of the IOP. At the 8-week mark, we found that the survival rate of RGCS reached 80%. Further research revealed that NGF-chitosan enhanced the survival rate by inhibiting the apoptosis of RGCS. We injected CTB into the vitreous body of the eyeball to observe the long-distance projections of RGC axons. Compared with the LC group, the CTB signals in the optic nerve, LGN, and SC were significantly enhanced in the NGF-chitosan group. We elevated visual function through electrophysiological testing. We measured both FVEP and PHNR, and the results indicated that NGF-chitosan effectively protected visual function. The aforementioned results demonstrate that NGF-chitosan can protect RGCS. The question then arises, can NGF-chitosan induce the regeneration of RGCS? Previous literature indicates that After optic nerve injury, retinal cells in adult mouse proliferate and express nesting. This phenomenon indicates that there is a potential for neurogenesis in the adult mouse retina. In vitro studies, we discovered that nesting positive cells were indeed present in the retina, and these cells could form neurospheres during the culture process. Moreover, NGF-Shattuson was capable of promoting the proliferation of these cells. When cultured in vitro for 14 days, nesting positive cells could differentiate into TOG1 positive cells. The differentiation efficiency in the NGF-Shattuson group could reach 26%. We further validated retinal neurogenesis in vivo. The results showed that there were nesting positive cells in the retina, and the NGF-Shattuson could promote their proliferation. Some of the nesting positive cells could first differentiate into TOG1 positive cells, namely neuron-like cells. We further observed these cells using lineage tracing. We employed nesting ciliary to lose TD tomato mice. Upon tamoxifen induction, nesting expression would be triggered in retinal cells. In the NGF-Shattuson group, neuron-like cells expressing both TD tomato and TOG1 were observed in the retina 3 to 4 weeks post-treatment. At 6 weeks, TD tomato positive cells expressed BIN3A, indicating that these cells had differentiated into RGCS. At 8 weeks, TD tomato positive cells expressed NeuN, suggesting that these cells had differentiated into mature neurons. We employed patch-seq technology to investigate the morphology, function, and gene expression of these cells. This technique can provide multidimensional information about the cells. These TD tomato positive cells were capable of forming functional circuits. We examined a total of 68 cells, among which 64 cells were able to generate photoresponses. Further investigation revealed that 16 were of the on type, 19 were of the off type, and 5 were of the on-off type. Gene testing was conducted on TD tomato positive cells, and the results showed that the majority of these cells expressed markers of mature neurons. Surprisingly, these cells also expressed some markers of neuroprogenitor cells, indicating that a portion of them was still immature. This finding further suggested that these cells were newly generated. In summary, our self-developed NGF-Shattuson not only protects RGCs, but also promotes their regeneration, thereby offering a novel therapeutic paradigm for glaucoma treatment. Okay, thanks for your attention.
Thank you, Liu Xiao. And we would thank all the speakers for sharing their pioneering work and insights.